Hey guys, thanks very much for tuning in again to this next video on planes, on plane and descriptive geometry. As you might see there on the screen in front of you, there's quite a lot to go through in this video, so it's going to take a while. It'll be a long enough video. I'm going to go through, I think there's 9 models, 2, 3, 4, 5, 6, 7, 8. I have 9 models here all in this one part on SolidWorks, and I'm going to use those 9 models to help me to teach my way through 9 different practices and sets of principles, really, which might help us to solve some of the common questions in plane and descriptive geometry. In the previous video, we dealt with simply inclined planes. We rebatted simply inclined planes about their horizontal trace and about their vertical trace. Towards the end of the video, we got onto some more difficult questions where there was some oblique planes being brought in. But now we're going to kind of get on to more interesting problems, and I suppose problems that really involve a bit more thought and a bit more understanding. I'm going to roll back along my feature tree here, and I'm going to go right back to the very first one here on the left hand side. We'll have a quick look through the model. First, we're going to flick over then and go to the worksheet that I have that I'm going to be working through, and that's really the way that the whole tutorial is going to go. I'll be working between SolidWorks and worksheets, flicking over and back maybe every 3, 4 or 5 minutes. This is really a continuation from the last video. So in the first video here on planes, I know there was a question there where it gave us a lamina. We'll just say A, B, C was the lamina, and a lamina is only a portion of a plane. So it's a certain set portion of a plane, and in this case, an oblique plane. And the question the last time was to find the edge view of the plane, and then, of course, find the vertical horizontal traces of the plane. The last time we did that by extending an edge down until it hits the ground, until it hits the horizontal trace, and extending a second edge down to hit the horizontal trace. And then our horizontal trace, well, if we have 2 points on the trace, we can draw the line, we can draw the trace. Then a horizontal section through the top point gave us a point for the vertical trace. There's a different method I want to use this time. And the first thing I have drawn here is I have the actual lamina in. That's the elevation of what it looks like. Then they're projected onto the vertical plane, and there is the plan of what that lamina looks like projected down onto the horizontal plane. So that's what we have on papers. We have the two-dimensional views, but here in SolidWorks we also have this 3D view of the object dropped in. What we do this time is we're not going to extend on. We're not going to start extending edges. I'd like to see a second method of doing this, and the method is like I've just done the method in 3D. Like in 3D, I will be able to find the traces of the plane if I can find this view right here. If I can find this view where the plane appears as a single straight line. I'm a little bit off there now. 1 second, around there someplace. If I can find a view where that lamina appears as one single straight line, so all 3 points A, B and C are linear, and I can extend it down then to hit the ground, that'll give me the trace, a point view of the trace, and it'll give me an edge view of the whole plane. That's what I'm looking for. So the way we might do that, like there's 2 ways really of finding the edge view of a plane, but I'm going to go with this method. In the elevation, I'm going to draw a horizontal line. What we could also say is that we're cutting the object horizontally. So if I put a section plane in here, parallel to the top plane, through this point right here, I'm cutting the object horizontally. And of course, if that is a horizontal cut, if I just turn my view around, well, that horizontal section I just put in right there, if I see it now in plan, well, that's a true length line in plan because it's a line parallel, or the section is parallel to the horizontal plane. So the horizontal section gives me a true length line. If you look along a true length line on a plane, you get a point view of the line, you get an edge view of the plane. So let's use that method. So my horizontal section through the plane will reveal a true length line in plan. So that green line right there is my horizontal line that lies on the plane. There's the projecting down to the XY and then down through to plan. And there is the green line. So that's my true length line that lies on the plane in plan. And then there it is in the actual three-dimensional view. So that right there is a true length line that lies on the plane. If I can find a point view of that green line, so I'm looking at an angle now along the line in plan and along this, because they're parallel, of course. So if I can find it as a point view, when that line becomes a point, the plane becomes an edge. What does that look like? Well, first of all, I'm going to have to extend on my ground, my horizontal plane, because I need to project right through along that line. I need to project up along the line and drop in an x1, y1 anywhere you want. Now, of course, when we do this on paper, it's going to take a slightly different form. It's going to look like this. So it's going to look like that. So we'll project up along in line with the green, the true length line in plan. We'll drop in our x1, y1 line at 90 degrees to our projection as always. And finally, that right there, the x1, y1 is the position of an auxiliary vertical plane. So there we have our AVP, and I think I will label in, yeah, my AVP, my auxiliary vertical plane, or an extra vertical plane, auxiliary meaning extra. There's an extra vertical plane in there that will give us some different information on this object. Now, next we're going to, I just dropped in the labels there, I should have put them in as an earlier stage, my vertical and horizontal plane. But next what we're going to do is we're going to start projecting the points on. Now I'm working just with the 3D here, so I've projected in line with that green and I've projected all of the points. Now what we're seeing in SolidWorks is the exact same really as we'll do on paper, but you know, it's going to look a bit different. It's obviously, it's very graphic here, it's great to see it, but this is the 3D, we'll see the 2D on paper soon. When we project all of the points up onto that auxiliary, well, we find that the 3 points are perfectly in line. We get an edge view of the plane. If I extend that edge view and make it a little bit bigger, so I've extended it there in blue, I've gone down to hit the ground and I've gone up, just extended anywhere up at all. That extension right there, that's an edge view of the whole plane, the full oblique plane. And it can keep going on as far as you want, but the main thing is it goes down to ground, and if it's going onto the ground here, I can come back with that point. So let's just have a close look in at what's happening from this point here. If I project back from that point, I have my horizontal trace. That is right along there. That's my horizontal trace where the edge view is, and again, like the last time, we just extended a line and got a point on the trace and extended the second line and got a point on the trace. This time I'm finding the edge view of the plane and extending the edge view to get my horizontal trace. After that, I could use a method like we will be using quite a bit there soon, okay? We'll be using, sorry, no, here, our method here that's in yellow, just like we used, actually, we used it in the last video. A horizontal section will give us a line parallel to the horizontal trace. So parallel to the horizontal trace, and then across there in the elevation, maintaining its height, that gives us a point that our vertical trace can go through. And there we have our vertical trace. So the horizontal section put in right there. There's different methods we could have used. We could have also taken a point on the plane, which I will be getting onto there. I think it's actually in the second model, not the next one, but the second one after that. After that, we're pretty much there. The last part is on SolidWorks, just for a bit of clarity. I've just dropped in what the plane looks like, my blue plane, and again, any size at all. Now, to just turn this guy around again, I'm going to look along that green line, the true length line right there. I'm going to see the red edge view of the lamina, and I should see that my blue plane, the whole oblique plane, lines up perfectly with the blue edge view that I've extended up and extended down, finding the horizontal trace right here. So if I just turn it around again, we should see that everything lines up pretty much there. Where are we? There. So there we are. that's the bit of understanding that you need to have behind this method. So we could either, as I said, the first method which we practiced in video 1 at the very last question of video 1 was extending a single edge or a single line on a surface to find a point on the trace. And this one here involves taking a horizontal cut or a horizontal line through an object, and which becomes a true length down there in plan. Look along the true length, get the edge view and extend that. So let's go back to our drawing board and we will give this a go. We'll see what it looks like. I have a question set up with 3 coordinates, A, B and C, and let's see how it works. So guys, in this first question here that we're going to do, it's very similar to a similar style question to what we finished up on in video 1. I've given 3 coordinates here for points A, B and C. A here is it's on a 0. So first of all, this was actually the starting point for the whole drawing. Up 80 mil from the bottom of your page, and you can draw your XY. In 150 from the left. That's the starting point and the reference point for all measurements for the 3 coordinates of the points. So A is on the 0 mark. It's up 8 and it's out 38. B is 30 in, 78 up and 23 out. And C finally is 41 in, 43 up and 64 mil out. So there's the starting point of 80, 150 and the coordinates of all 3 points given. The last question we did in the previous video was this one right here, where we extended an edge down through to find a point on the ground, and that has to be a point in the horizontal trace, and we extended a second time, and where we got the common points we extended through to get our horizontal, and we finished up here with the pink detail, which is a horizontal section cut through a point, giving us a point on the vertical trace. An alternative method for this, as you've just seen there in SolidWorks, is taking a horizontal section cut through the plane, or a horizontal line lying on the plane, whatever way you prefer to call that one. I'll just highlight this with a colour as well. Right there, that is a horizontal line that lies on the plane, or it's a horizontal section through the plane, whichever you prefer to call it. That finishes at point 1. Point 1 is on the line AB, so I'm going to find point 1, which is on the line AB. Down here in plan, I'm going to draw, it goes from C to 1, I'm going to draw point C to point 1. I'll draw it in pencil and then I'll just highlight it there. And that right there is a true length line. So we now have a true length line on a plane. If you look along a true length line on the plane, you get 2 things. First of all, you get a point view of that line, and second of all, you get an edge view of that plane. So we need to view in this direction, looking along that true length line. I'm going to just use my adjustable here to structure this and to help me to get my accuracy. No need for sliding set squares if we can. Adjustables are much better. But take your time, line it up, check it, make sure you've this pretty accurate. We don't want to be building up an inaccuracy already. We're going to project through point B there, taking it all the way up my page. Point C and 1, which are both linear, and point A. I want to make sure now that I need to drop an X1, Y1 line up here someplace. Will it fit? I know that when you project from a plan, you get an elevation. This elevation is going to be the same height as this elevation. So I need to just make sure it'll fit. At that position, it should fit just fine. You could measure this if you want, but I think a very quick little look like I just gave there is usually enough. That right there is the X1, Y1. Or it's the ground line of this auxiliary vertical plane that we're going to draw right now. So we have an auxiliary vertical plane up here, and basically our drawing is built from this ground line up. The heights, as I said, if you project from a plan, you get an elevation. The height of this elevation is the same as the height of this elevation. Nothing changed except we moved from the front around to the side and looked at the object. The object did not change height. I'm going to start off with the highest point there, that being point B. And take the height of B from projection of B. I'm going to go down to my next point, which is C, and I'll take the height from the ground up, from the XY line up to C, and I will project up. The height of point 1 is the same, so it falls on the same point. That's a point view of a line right there. The height of point A is the last one. From A and here. So we get point B up at the top. We get point C, comma 1 in the middle, and we get point A on the ground. Just like I did in SolidWorks. I'm going to join my 3 points. So B, C, and A, and hopefully the accuracy is fairly good with you here. That is an edge view of the plane. I'm also, in the same color I used on SolidWorks, while I'm here and while it's set, I'm going to extend on the oblique plane up and down. I'm going to take note of this right now. That right there is an edge view of the lamina, first of all, plus the oblique plane. So it's an edge view of the lamina, but it's also an edge view of the oblique plane. Really, really, really important point right there. So if we've looked along the point view of the line, if we've looked along the true length line, we get point view of line C1. Another really important point right there. What else? What's on the ground? It's an edge view of the HP, the horizontal plane. It's an edge view of the ground because the object is built up on the ground. And the final point I'd like to drop in here is this one right here. If we're seeing an edge view of the plane, and if we're seeing an edge view of the ground, we see true inclination to horizontal plane. We see the true inclination that it makes to the horizontal plane of T. Just written out fully there. It's the true inclination that the plane makes to the horizontal plane. When we see an edge view of the plane on an edge view of the ground, we see a true inclination that the plane makes. I think actually the final point I should put in right there. We'll load this up with notes. There'll be plenty there to revise back on. If I'm seeing in an elevation, if I'm seeing an edge view of the plane, I must be seeing a point view of the horizontal trace. So I think that's the final point, as far as I know anyway, as far as I can think, unless I've forgotten some more, but I don't think I have. We can, if you would like to, and if it helps to relate it to SolidWorks here and to what you've seen in SolidWorks, you can just fill in that is the AVP, if you like, if that helps to relate it all back to SolidWorks. So that's our auxiliary vertical plane right there. I have a point view of a trace, so I can bring that trace down. I can take the point view of the trace, which is on the ground, and actually bring it on down a little bit further, and I can project it back down. That is the trace in its full position, and the trace is the horizontal trace, the HT. So that's a really handy way to do this. Finally, and to get this question wrapped up and onto our next one, I'm going to do a horizontal section cut through point B, I suppose. That's how I'm going to solve the rest of it and get the vertical. So a horizontal section cut gives us a line parallel to the horizontal trace. So from B, parallel to the trace. It's a horizontal section cut, as I said, so it's going to just look horizontal here in the elevation. And somewhere along that horizontal section cut, I should get a point on the trace. That point is defining my vertical trace. That's the end of that question. So to recap, instead of like the last time, the last video, last question of it was sheet 16, we extended an edge along a plane, and that could have been, as I said last time, it could have been point B down to this random point right here. As long as we found that same random point on AC down in plan, point B would still land in the exact same place on the trace. This time we found an edge view of the plane using an auxiliary. That edge view was enough for us to establish and increase the plane, extend it going up and down being the important one, and get a point view of the horizontal trace, projecting that back down to plan to get a full trace on the ground, and then finally using our horizontal section cut to get our vertical trace. I'm labelling that sheet as just that. The last one was sheet 16. I'm going to call that 16 part B there. So it's just an extra add-on to the last sheet that hopefully clarifies another little area that we need to know. Moving on ahead. Next question I want to go through here is on sheet number 18, and it is intersecting oblique planes. So two oblique planes, one here facing the left and one here facing the right, and I want to see what the line of intersection is, and I want to find out what the dihedral angle or the true angle that those two planes make. We'll start off by giving the wrong answer, I suppose, because we'll see it so often. This is not the line of intersection. If it was that easy, it wouldn't be on the higher level curriculum. So let's see why that's not the line of intersection, and let's see what is, and we'll see how we deal with this. We need to work on visualization here as well. So back to SolidWorks for a while, and then we'll be back onto this sheet, and I'll have this ugly looking line here rubbed out, and we'll do this right. Here we are, so with our second model, and again we're on the vertical and horizontal planes. And if I just pop in that first plane right here, this blue plane represents the oblique plane that faces towards the left hand side. I suppose it's pointing towards the left. I finished it off with this nice curve here. On paper they don't really do that. It would probably overcomplicate what's happening in the drawing. We need one more oblique plane dropped in, and that is here. When it does pop up, there we are. So there's the oblique plane, the green one facing towards the right hand side. We see a vertical trace, and then the second vertical trace there on the vertical plane, and the two traces cross at this point. And down the ground we see our horizontal trace of the blue, the horizontal trace of the green, and they both cross at this point. That is 2 points of intersection. So in 3D space we know that that is the line of intersection. The big difference here is this though, and pardon the fact that the model is so big that I have so many models on it now, but right there, that's what the line of intersection looks like in elevation. You see, the thing and the harder part to understand here is that as we move it around in plan, you know, it doesn't always work out. So if I just keep the cursor, if I go back up to elevation right here, I'm thinking of drawing this line. Well, that is the correct line in elevation. Or in elevation, it is where the two vertical traces cross. In elevation, it is where the two horizontal traces cross. Okay, so what we need to think about is, as we look at the elevation of the object, that is the complete line. As we look down at the plan of the object, watch where this point goes. This point becomes part of the XY line, because that XY line along there represents an edge view of the vertical plane. That is the point on the vertical plane where the two vertical traces cross. That is the point in plan where the two horizontal traces cross. Where does that go when I go up to elevation? So just watch this point. When I go back up to elevation, that is the point on the ground where the two horizontal planes cross or intersect. So we're going to have just a good think about it as we're doing it. We won't fall into the trap of that one single straight line down through. We have a plan and an elevation. You can see this black line, this line of intersection in elevation. You can see this line in plan. You can see them as two separate lines. Basically, it's two views of one line. So we need to draw them twice. We're not going to just fall into the trap of joining the point in the elevation straight down to where the point is in plan. That would be just completely wrong. That might help just to identify and to visualize what the two planes look like. Not really a whole pile more to go through on this model, apart from when it does come to time to get the dihedral angle. A dihedral angle comes from a point view of a line of intersection. That is, the black line is the line of intersection. I'm going to have to go about finding a view where that line appears as one single point. And if that appears as a point, my two planes appear as two edges, and I get my dihedral angle, my true angle between the two planes. That's it. Let's go back to paper. Let's see what we're doing next. So back here on the worksheet, as I said, we're definitely not going to fall into the trap. That point right there represents where the VT, and there's the H there, and I'm going to call that V1, T1, and H1. That point represents where the vertical traces cross. As we look at the elevation of the objects only, where do the horizontal traces cross? Well, the horizontal traces cross on the horizontal plane, of course, down here. Where is the horizontal plane when we look at an elevation? The horizontal plane is right there. As you look in at an elevation of an object, the XY line is the horizontal plane. It's an edge view. Don't forget the horizontal plane extends out from the XY line. We're seeing an edge view of everything that happens on the horizontal plane. That point lies on the horizontal plane, so we get our line of intersection right here. That is my LOI, line of intersection. What about down in plan? Down in plan, we're seeing where that point is. We're seeing that the two traces cross, and that is a point on the line of intersection. When you look down at a plan of an object, again, forget about the elevation here. When you look down at a plan, you are seeing the XY line as a representation of the vertical plane standing out here from my page. The vertical traces cross at that point. That point is on the vertical plane. So take it down to the vertical plane and draw the line of intersection. As I said on SolidWorks, when you're looking at the elevation, you see the full line of intersection right there. When you look down the plan, you see the full line of intersection right there, LOI. So we certainly don't want to fall into the trap of assuming that it's just this one big straight line. The question is not that easy. That right there is enough. That's all we need to do. There's nothing major about this, or nothing majorly challenging about just finding that line, but we could be forgiven for just really forgetting that there's any bit of difficulty to this question and just joining point to point straight away. I'm going to pause the video, add just a little bit of colour onto the two planes. I have found the line of intersection. The next thing is to find the dihedral angle. So I'll just pause it, add some colour, and then come back with that. A bit of colour is added there now, which I think helps to understand what's happening in the two views. We can easily, I think anyway, we can easily see now why that point has to line up with where it is in the elevation, and this point has to line up with where it is in plan. Find the dihedral angle between the two planes. For the dihedral angle, you need two things. Okay, so for dihedral, as always, two things. Number one is the true length of the line of intersection, and then number two is the point view line of intersection. That's if we want to do the two-step dihedral. There is of course a one-step method, which I might just do here as well on the very same drawing. The two-step dihedral is to find the true length of the line of intersection, and second, find the point view of the line of intersection. Just to help this to stand out a little bit more now that the colour is in there, I might just go over the line of intersection in plan and in elevation. I'm going to go ahead and I'm going to find the true length of the line of intersection. We'll find the true length of a line by looking at 90 degrees to that line. Set my adjustable parallel to the line. And then look 90 degrees to that line. I'm going to break these down a little bit. You know, we're only on a little A4 page here. I'm not sure how much space we'll even have for the likes of this view, but I'm going to break these down and just take those points, and I'm going to take this one right here to the front. So the points I'm taking are these two on the ground, this one on the ground. That's point 1, that's point 2, point 3 on the ground, and point 4 on the ground. I'm going to just drop in my x1, y1 line, and then I need to figure out what height my points are at. Point 1 is on the ground, which is right here. Point 1. Point 3 is on the ground, comma, 4 is also there. Whereas point 2? Point 2 is at that height right there. That's the height of point 2. So I just projected it from the line onto the line. So there's point 2, and there is point 2. Hopefully it will bring a bit of clarity if I just do this. Point 3 is on the ground and point 4 is on the ground. I'm breaking this question down a little bit smaller than it currently is, because I'm not quite sure if we're going to have enough space for it. I've broken it down into this, a portion of each surface, there and there. So I still have a portion of one surface and I have a portion of the other surface, a portion of the blue, a portion of the red, and that just looks like this in plan. Heights of points, so what do I need to take a height of? Just number 2, that's it. So number 2 is at a height from there, from the XY line up to number 2. And again, just like the last one, we project from a plan, so that's an elevation, and elevations have the same common heights. That's point 2. The line from 1 to 2 is true length line of intersection. Now, you might just say there that, oh no, that's not the true length of the line because the whole line isn't there. Yeah, well, you'd be 100% right. It's not the true length of the full line. If I wanted to take the rest of the line, I would see the whole thing as a true length. Then my drawing would be stretching all the way up to here. So I don't know if I'd have enough space for that. I don't think I would. Just for understanding, I'm going to maybe add in this guy right here. I'm going to go over the XY line. My x1, y1 I should call it. If I'm looking in from this angle at the object, well, I know I'm dropping everything. If I'm looking in from this angle, I'm projecting at 90 degrees to the line of intersection, the LO, I right there. And then my x and y1 is at 90 degrees to my projections. The surface I'm seeing is red. So that right there is a portion of the red surface. So I'll just add my bit of colour in there. Why can't I see the blue one? Well, I can't see the blue one because it is directly behind the red one. It is directly behind this one, so it's completely overshadowed by the red surface. And I can only see a portion of the surface. I could keep adding on, and if I had an A3 page here for this question, I would have definitely taken the full thing, but that's all I think I can afford to take right now. Next thing I'm going to do is I'm going to view along the true length line. So step 1 up there. Step 1 was to find the true length of the line of intersection, or a portion of the line of intersection, and step 2 is to find the point view of the line of intersection. To find the point view of a line, you look along the true length of that line. So here we go. That's the angle of the true length. There. I'm going to go ahead and look along it. Along. I'll drop in my x2, y2. And then it's time to set some distances. Now the first thing I want to check is what we'll do. I want some measurements up here. I'm going to skip one view and work from the XY line back. Don't make the mistake. Don't skip 1, 2, 3 views and then work down or something crazy like that. We want them in this view, so we'll skip one view and work back. Let's just see will the biggest points fit. Number 3, does it fit? It's gone just off the border, but it's fitting quite okay. So I'm gonna go with it now. I could put in a reference line as well and shorten everything up. I'm not going to. I'm going to stick with it for now. 0.4 on my blue surface is the first one. I'll take the distance from 0.4 and mark it up on this XY. So that's 0.4 right there. What's next as I open out then along that? I have point number 2 right here. So where's 2? 2 is there. So I'll take it from the XY again. That's number 2. What I'll also find is that point 1 should be the exact same. And point 1 is the exact same. So we get point view of the line. So that is 1 and 2 right there. I think I might need to extend on that projection a little bit there. The one that I had drawn here. Final point that's missing for me is my number 3 on the red surface. So I have a point on each surface and I have the 2 points in the line. That's the distance back to 3, distance out to 3. Now 4 to 1 and 2, if I don't drop everything here, 4 to 1 and 2 is blue because that is the blue surface. Okay, that is an edge view of blue oblique plane. Three is on the red surface, so 3 going up to 1, 2 is an edge view of red OBL PL oblique plane. And finally, right there is a dihedral angle. And I would always suggest, whether you're asked to or not, take the 10 seconds to go ahead and much more carefully than I will do right now, measure up your dihedral, but don't, for God's sake, don't call this big angle here 62 degrees, call it 118 degrees or whatever that is, 117 I think, dihedral angle 117 degrees. Don't read the scales the wrong way. You see it so often, such a mistake at this stage. Now, the usual thing I tell students here is that, you know, if it says find the line of intersection, find the dihedral, you know, it's hard to know, find it. Yeah, we have it found. If it says to state or note the dihedral or determine the dihedral, you know, depending on the wording of the question, sometimes you are required to write down the exact dihedral angle, well, plus or minus a couple of degrees, of course. Sometimes you don't have to write it down. I would always put it in there. If you go to the trouble of projecting your first and second auxiliaries, will you go ahead and put in your dihedral angle? It is just so much easier. If you want to stop at this point in the video, stop. If you want to see the one-step method, stay. Okay? The one-step dihedral, I'll have it added onto this drawing within a few minutes. We find, number 1, true length of the line of intersection plus add in a plane. And that's it. We add in a plane at that point. Okay, so where I have my true length of the line of intersection, and don't confuse this now, the question is done. I have answered what they want me to answer. But if I wanted to do the dihedral angle in a different way, I can use everything I have here, and I don't need this second step. For the one-step method, this is what we do. We take the angle of our true length line, which is right here. Have I colour for this job? I have. I'm going to try and hopefully see if an orange will stand out enough here. We have the angle of our line, and I'm going to put in a plane perpendicular to the line. I'm going to use 3 and 4 as the base of this plane. Orange is definitely not going to stand out. I'm going to go with black. I've just dropped a plane, which is a triangle, of course. It's going from point 3 on the ground. It's going up to the top here, and it's going back down to the ground again. I've put that in now perpendicular to the line of intersection. If we want, and I certainly wouldn't do this in an exam situation, I will do it now because hopefully it'll help with understanding. But if we want to, we can draw the plane in its original position. So I won't change my adjustment for the sake of one line now. That plane hits the line of intersection here. So that plane in its inclined position right now where it stands is there. If it's inclined and it's standing up against the line of intersection, well, we're not really seeing what's happening. We're not seeing the true dihedral angle. But if I can take that plane and just rabat it and drop it down onto the ground and then draw it, I see a dihedral angle. One step. It's all happens here. No need for your second step. So let's rabat it. Let's see what it's going to look like next. If I just pick my compass up off the floor, and for some reason the lead isn't broken, I'm going to take the point view. First of all, we need to recognize here, if we just really bring this all into the oblique plane now and think about this, that line right there is the horizontal trace of that triangle. And I have already looked along that, so I have a point view. The point view up to the point of it on the line of intersection can be rabatted down. Well, the hinge line never moved. The hinge line stayed exactly where it was. 3 and 4 stayed where they were. But this point up here, I'm going to call this point number 5. Point number 5 has moved from its original position there, and it has moved right down onto the ground here. So let's go ahead and project that, and we'll project down at the same angle we projected up earlier. Point 5 has moved perpendicular to the hinge line, as always. That is now point 5. Point 5 reveals for us the true shape of the plane that was laid in perpendicular to the line of intersection, meaning that right there is the dihedral angle. If I just note that equals dihedral angle. And if I measure this, and it's just time for me to expose how bad my accuracy is here in this drawing. Of course, it is the exact same number as before, or it's it's within a degree or two. But I'm going to spoof my way through 117 degrees exactly as it was before. I think it's actually reading in as about 119 or 118 or something, which isn't bad for, a degree off between the two. Putting our plane standing in perpendicular to the line of intersection, rabatting that plane onto the ground, and the whole idea of the rabatment is I want to find the true angle. I want to find the true shape of the plane, and the true shape of the plane gives me the true angle of the plane right here. That right there, that rabatted plane is enough to solve my dihedral angle question. I hope this video helps. I know there's quite a bit, or this portion of the video, should I say, that is only the second object of 9. You're in it for the long haul. If we have a look at what's coming up next, really taking off now from what we did in our first video, and this time it is rabat the given oblique plane about the horizontal trace, sheet 19. There's 3 sheets in a row named or with the very same wording of question. I'm going to go through 2 of them to rabat the oblique plane about the horizontal trace, 2 of them, and on the third one I'm going to rabat about the vertical trace. So 2 different methods of rabatting about the horizontal trace, and then we'll just do the one and the vertical. So back to SolidWorks now for a few minutes. Now we're back here again in the world of SolidWorks, and I've my oblique plane dropped in here, my vertical trace, my horizontal trace, and this lovely curve back on the oblique plane. Again, the oblique plane can be any size at all that you want. The question this time that we're trying to work with, and the bit of understanding I need you to take from this, is rabat the given oblique plane about the horizontal trace. So basically, take this plane, detach it from the vertical right there, put some hinges here along the horizontal, and flip it out onto the ground. if it was only that simple. But it is actually quite simple. We'll have no problem at all. We're going to be using some of the theory that we learned there just a while ago on this particular question. We'll be using some of the exact same methods now, and we're going to apply them to this question and see how this works. So we're batting this plane down onto the horizontal and about the horizontal trace right there, and you were batted right out onto the ground. Why would this be important? Well, if there was a little three-dimensional object dropped in here, maybe a cylinder coming up and being cut by the plane, or a cone or a pyramid or whatever the object might be, we might have to find a true shape of the cut surface. So we'd have to be able to do maybe a rebatment, would help us here as well. Let's get going. First job I did was I extended the horizontal plane going right back there, because I know this drawing is about to get pretty big. I want to first of all find an edge view of the plane, and if I have an edge view, I have probably got a point view of a line, and that means I can do a rebatment. To find the edge view of the plane, just like in the first question we did in this video, if we can turn it all around until we can find that trace right there, if we can find that trace, the horizontal, as a point view, we get an edge view of the plane, which means we can basically see a point view of the hinge line. We can drop our compass, we can swing it down onto the ground, and then that will be the question solved. So take your look along your line, project along your line there, pick a point and put in your x1, y1, put in your auxiliary vertical plane. And I think I probably have that. There's the x1, y1, and there's the auxiliary vertical plane label. Next thing is this, just so that we all remember this part. That is a point view of the line. I don't know the true inclination of the plane, so I can't just draw the plane right now. I need to find a point up along that plane someplace. So I've picked a completely random point right here on the vertical trace. So look at what I'm doing here now. I've picked a completely random point on the vertical trace. I'm going back to find this view where I can get a point view of the horizontal trace, edge view of the plane. And that point that's on the trace gives me the rest. If I have a point view of the horizontal, and if I have a point that lies on the plane, well, there we go, we can draw the line. So what do I do? How do I get that point? Well, in SolidWorks, I could easily just hit 3D sketch, draw the line, and that's it. But on paper, what do we do? Well, we bring it down to the ground. Okay, down to plan, basically. We're bringing it from elevation down to plan. We're projecting from its position in plan up onto the next x1, y1 line. And then we're taking our height from elevation. And look, here's the one-step method that SolidWorks could do for me, but that's no good on paper. So we bring it a point P on the vertical trace. We bring it down to plan. We project, and we take the same height from the XY line up as the original, because of course this is an elevation we're looking at, and this is an elevation we're looking at. That gives me an edge view of the plane. If I have an edge view of the plane, I can rabat. I can rabat about the point view of the horizontal trace, which is right here. So there we go. There's my rebatment. I didn't bother with anything else up there because really I don't need to. You know, this is unlimited. We could keep going out and out and out and keep getting bigger and bigger settings with the compass. Or, of course, SolidWorks will allow me to make this unlimited, but I just worked with the point that I had. I worked with point P right here. And I rebatted point P down onto the ground, and in its position on the ground, like this is the 2D, and in 3D we'd be catching this guy and dropping it and hinging it out on the ground. So let's do that. First of all, we need to project that back to plan. If we did do that, what would it look like is the big question. It would look like this. Okay, that's what it would look like right there. That is the hinge line. So what I've just drawn up here in this view, I've just drawn it again in position right here. Okay, but the movement that happens whenever you do a rebatment, every point moves perpendicular to the hinge line. So that's a 90-degree angle right there. I have the horizontal trace which stays in position. That's the hinge line. The hinge line never moves. That stays in position. The vertical trace has been dropped out onto the ground. So there we go. Where is it? There's our plane. That is the plane in its rebatted position. And as far as I know, I think that is it for this one. That's probably onto the next one right there. The other thing to look out for, okay, there's this sheet is shown twice. And instead of popping back to this SolidWorks again, I want to just show one little piece of information right here. I'll just do it right now live in SolidWorks. This line here is 130.5 millimeters. That is by complete chance. There is no significance to that distance apart from the distance up along the vertical trace up to the random point is 130.5. Okay, I'll accept that. That's fine. If I wanted to check down here, the distance along the vertical trace to this point is 130.5. It has to be, because the distance up along the original vertical trace to the random point has to be the same as the distance along the vertical trace to the random point again when it's in its rebatted position. We'll keep that in mind. Okay, that's what we're going to use to solve it in a second method. The first method we're going to use right now, we're going to go ahead and get an edge view of the plane. We're going to pick a point that we'll already have picked to find the edge view of the plane, and we'll rebat that point down perpendicular to the hinge line. On our second sheet, we'll do something similar, but it's that 130.5. Now, that's not the measurement I'm going to use on paper, but what I'm saying is that the fact that the distance up along the vertical trace up to the point here is the exact same as out along the vertical trace onto the point here. That is one extra little thing I want to keep in mind when I move on to, I think it's sheet number 20. That's it for SolidWorks this time. Let's get back to page 19. Let's take what we had there, so on SolidWorks, let's solve a question with it. First thing is, we need to look along the horizontal trace to get an edge view of the plane. So I'm going to set up my adjustable here in line with the horizontal trace. I can probably label my traces as well. I suppose it would look good in the video. There's the horizontal trace right there. There's the vertical trace and the horizontal trace. I've set up in line with the horizontal trace. I'm going to project along the horizontal trace. I'm going to set up a perpendicular line for my x1, y1, right there. I'm going to do what I did in the video, exactly, absolutely no change. I'm going to take a completely random point P on the vertical trace. I'm going to find that point in plan. So as we had in the previous question there, where is that point in plan? Well, that is on the vertical plane, and in plan the vertical plane appears as there, the xy line. So there's point P in plan. If I just put that in brackets, point P in plan. I'll project the point because everything comes from plan for this drawing. Up in that drawing right there, I have in that place right there, I looked. This is my viewing angle right here. I looked along the horizontal trace and I got a point view of the HT. The height of point P in one elevation is the same as point P in the second elevation. So let's go ahead and we will get the height of point P and mark it. And that gives me, from the trace to the point P, and extend it as far as I want. Gives me an edge view of the oblique plane. It also gives me true inclination to the HP, or the ground right there. What else should I label? I should probably label the blue point P just for a bit of continuity here. That is point P right there on the plane. So there we go. That's an edge view of the plane. Let's go ahead and do the rebatment. I need to put the rebatment onto the ground. What's my angle here again? There we are. I need to put that rebatment down onto the ground, so I'm going to extend on that ground a little bit because it's not quite big enough as it is. I'll take the hinge line, and the hinge line appears as a point view there in the auxiliary. And I'll take point P and I'll hinge it down on the ground. I need to find where that point P landed on the ground, so I'm going to project it back down to plan. There. And finally, there it is, going back down to plan. So there's my hinging happening until it lands on the horizontal plane, and it goes down to plan. And of course, anything on the horizontal plane appears as a true length, true shape, and true angle in plan. The final step is, there it is, there's point P in plan, and everything moves in a rebatment. Everything moves perpendicular to the hinged line. So there we go. That is point P right there, labeled again. So what I've done is this. I can join from the corner down, and I can just go ahead and there we go. That is the true shape. Of the oblique plane. There's a little one that might be asked. They might not ask you for the true shape of the oblique plane, but they might ask you for this one though, where you have to go and find the true shape anyway. They might ask you for the true angle between the traces. That has to be the true angle between the traces. If you're seeing the plane as a true shape, well, then you see the true angle between the two edges. So there we go. That is the plane rebatted down onto the ground. It is a random point P. If I had picked a point P up here and brought it down and up and rebatted and out, it would have come out onto the same line. So the position of point P is completely irrelevant. If I went too far up, it wouldn't fit in the page, and if I went way too far down, it would be very, very hard to ensure that the angle of my line and everything subsequent to that would be accurate. So pick something that fits, but not something way too small. That is the true shape of the oblique plane. That is the rebatment of an oblique plane about the horizontal trace. And it is the true angle between the traces. The second one I was talking about, and really it's the same thing as that, but it's just that little bit faster, I think, than this method. If we have a look, and we're going to be using so much of the same stuff, but I'm going to skip all of this. I'm going to skip everything up here. Okay, the second one I was talking about is this. Pick your point P once again. Point P. Find that point in plan, just like I did last time, because, you know, don't forget, the horizontal trace has to stay where it is, so everything really is based on what's in plan here. There's point P. Not sure if these are a different angle. I'm not going to take a chance. I'll use sliding set squares and set up for this one. Project out. We're hinging it without the need for a full auxiliary this time. Okay. So we've just done the rebatment right now without the need for an edge view and for a compass and for swinging and the whole thing. So that's the rebatment right there, done for us. What I said was, well, from this point here up to point P, that distance is on the vertical trace. If it's on the vertical trace and it's in the elevation, well, it's a true length. That is the true length along the trace up to point P. Okay, if that's the true length along the trace up to point P, well, when we've taken this plane and dropped it down the ground, it's going to be the true length along the trace up to point P again here. So I've just taken that distance and I've brought it around. So in one simple step, and of course this is only if the question is worded in this way that we can do it like this. That is true shape of the oblique plane again. It is, of course, the same as last time, and I won't note it all here. I would if I was you at home. The true angle right there between the traces. Okay, I must drop it in, I suppose. between HT and VT. And there we go. That was the HP right there. That is the true shape of the plane, just skipping a whole load of auxiliaries and rotations and everything there. We've just achieved the very same thing on this page and on this page. So whatever one you think works best, I would definitely think that there's, you know, it's the same principles really being used in both methods. It's a slightly different application of that principle just here. It's kind of like a shortcut method that works just perfectly as well. Just know them all. Why not know them all? That's it for this one. And on to number 21 then. So that's 19 and 20, and they're both worded the same way to give you a chance to figure them out in two different ways. And what I'm going to do here is I'm going to change the word horizontal. So rabat the given oblique plane about the horizontal. I don't need to do it a third time. Vertical. Okay, so rabat that about the vertical trace, and I want to show this in our on SolidWorks first of all, the same as I'm doing all the time for these videos. I'll flip over there to SolidWorks for a few minutes, go through the model, and we'll be back here on paper to solve it right here on worksheet 21 after. The oblique plane is shown here again with our vertical and horizontal traces. So that's the very same one as we have, let's say, there on page 21 on our set of worksheets. We need to rabat the given oblique plane about the vertical trace. So this time the hinged line is down along here. We are fixing that line in position. We are going to take this line, we're going to just basically tear it off the horizontal plane right there, and we're going to hinge it up until it lands up here on the vertical plane. So you detach your horizontal trace and you swing it right up, swung about the vertical trace. The two methods can work again this time. You know, the two methods that I went through for the horizontal, for rabatting about the horizontal trace, using the full rabatment method, or just using the true length along the trace line as a part of a point and going perpendicular to the line. Both methods work this time, but for some reason, I think that, I don't know why it is, but when you start rabatting on vertical traces, it just takes that extra little bit of thought, I think, to ensure that you don't project the point from the wrong place. There's just something about it. And I think that anyone that's used to doing these questions will know that. But look, I hope I'll clear it all up now and have it just as well explained as I possibly can. We're going to be using the same method anyway. First of all, here in SolidWorks, we're going to be using the same set of principles really to solve this one as we did to solve this one. This one here, the hinge line was the horizontal trace, so I looked along the horizontal trace, I found an edge view of a plane, and I did my rabatment. This time the hinge line is the vertical trace, so I'm going to look down along the vertical trace, which means I need a little bit more space to work on down here. When I look down along the vertical trace, I project in line with it, I pick a point, and I draw my x1, y1 line. So I'm going to be projecting down along this vertical trace right here until I see that trace as a point view, until I see the plane as an edge view, and then at that stage, sorry if I just change it a little bit to there, let's say, at that stage when I can see the trace as a point view, I can grab the compass, I can swing it all the way around until it lands here on the vertical plane. Let's see what it all looks like. So I just have this, my auxiliary plane labeled here. It's not really unfortunately this time, last time there, that was an auxiliary vertical plane, so it's AVP. This isn't really an auxiliary horizontal plane as such, because it's not actually a horizontal plane, is it? But it's an auxiliary plane that stands at 90 degrees to the vertical plane. Where are we going now with this? We're going here. So we're using our method as before, but don't forget, this time, that's point P, because I need a point on the horizontal trace to direct the rest of this plane going out. I need to find, I'm projecting everything from the elevation here, it's down through the elevation, so I need to find that point as it appears in elevation. So I bring it from the plan up to the XY line, and then I project it through down to my view, and off the same distance that it was down into plan. Why do I do that? Well, because I just want that to line up with that. So if I just turn this again to look at my point view of the line, look at the way that the points line up perfectly. If I get a point view of the line, I'm getting an edge view of the plane right there on that point. That point, which is a completely random point on the horizontal trace, directs my plane. If we're thinking back to the previous steps in this one, if I have a point view of the trace and if I have a point on the other trace, well, I can just draw the, where is this? That's my 3D sketch right there. After that, I can just draw the edge view of the plane. If I have an edge view of a plane and if I have a point view of the hinge line, I can rabat. So there's my rabatment. Taking my rabatment back up into my main elevation right there is the next step. And finally, one of the final steps here is this: moving the point perpendicular to the hinge line. So as the point appears in elevation, sorry, no, where's that gone? As the point appears in elevation, I'll just look straight in from the front for a second. As the point appears in elevation, which is down here in the horizontal trace, it moves out perpendicular to the hinge line to get me a point on the vertical trace. And sure, once we have that, we have a vertical trace, and if we have a vertical trace, we have our plane rabatment. So there's the plane rabatment. Somehow it's just that little bit harder to visualize. Hopefully once we look down here now and we see the edge views and we see it all happening, you know, there it is, it's all happening right there. And we get, in elevation, we get the true shape of the plane. Of course, we also get the true angle between the vertical trace and horizontal trace. But there we go. This time we're kind of doing the same thing again. Really, we're batting a plane by using a point view of a trace in an auxiliary view, but it's just rabatment about the horizontal and rabatment about the vertical. Let's get back to the worksheet. Let's see this in action. And of course, before we do, if we had another copy of this worksheet, or if you would like to photocopy it yourself, the distance from this point right here out along the horizontal trace to hit that random point P, let's just say that's 140 millimeters right there. Well, I can be absolutely guaranteed that on my true shape over here, it's going to be 140 up to point P again. It has to be. My compass was set and it was swung out, so it has to have mapped the same length to the same length. So you could use that quick method again. I'm going to go through the full auxiliary method because I think that it's a bit more valuable and a bit more worthwhile. So back to paper again, and let's get this one solved before we move. As we said there in the video, and as we saw, what we're going to do first, once I have these labeled, my V, T, H, we're going to view down through the vertical trace. Let's get going. I'm going to view down through the vertical trace, and there's my angle. I'm going to go down through the vertical trace, and I'm going to take a 90 degree for an X1, Y1 line. Okay. What I've just found is a point view of the vertical trace. Point view VT. Next, I need a point on my horizontal trace. So there we go, point P. Where is that in the elevation? Don't forget, we're projecting everything from the elevation, so we need to find that in the elevation. So where is it? Well, it's on the ground in plan. It's on the horizontal plane, which is here in elevation on the horizontal plane. That is point P as it appears in elevation. Let's project this. What angle was I using? I was using this angle. Let's project it from the elevation down through the view. And that's, as you saw there in SolidWorks, let's take the distance from the XY out to the point there on the horizontal plane, and let's mark it. And there we go. We get a number of things this time. So it's time to do a good bit more labeling here. That is point P as it appears in my auxiliary plan. So auxiliary meaning extra, and if it's projected from an elevation, it is a plan. That is my auxiliary plan, and that is where point P appears to be. What else do I need to label here? That is an edge view of the oblique plane. Now, here's a big one. That right there is the true inclination to the vertical plane. It's when I looked down along the vertical trace, I found an edge view of the vertical plane. V of VP, love shortening names. Edge view of the vertical plane. And if I can see an edge view of the vertical plane and an edge view of the oblique plane, I get a true inclination. I think that's all of the notes and the acronyms I can fit on one sheet for now. Let's go ahead and rabat. So take the angle that we had our vertical plane at, extend it on up there a little bit because I need more space. And let's do the rabatment. We'll take the point view of the trace line. We'll take the point P, and we'll rabat it out right down along there. So we're rabatting this way. See here? I'm projecting back up at the same angle I came down. So in line with the trace, project back up. And finally, the point moves perpendicular to the hinge line. And there we go. That is the point P. And once we have the point P, we can go ahead and draw that. True shape of the oblique plane. True angle. VT to HT. And that's it. And I'm not sure if this helps. Sometimes some people love to see them. It just makes sense, and some people hate it and they don't like the look of it. There's the hinges. That's where it came from. It rabatted out from the ground up onto the vertical plane right there. And we did the rabatment using our auxiliary view. The auxiliary view that showed an edge view of the oblique plane and an edge view of the vertical plane. This auxiliary plan right here, which shows as well as a side note the true inclination to the vertical. We rabatted our point and brought it back up. And there we go. And just for proof, can we also see that second method here? Is the second method apparent in this question? Is the distance out along from the corner out along the horizontal trace, is it the same? Perfect. So the distance from that point in the corner out along the horizontal trace is the same on the ground in the plan where it has to be a true length, and in the true shape where it has to be a true length. So that is it for sheet number 21. There is our rabatment about the oblique, or about the vertical trace. Or alternatively, you might be asked to find the true inclination of an oblique plane, true inclination to the vertical, and there we are as well. So that's it for that one. These next ones here are really fast. I think that they're just dropped in there. I didn't bother doing SolidWorks on these. They're dropped in there just as a little extra for you, I think. And I'm not going to fully work through them at all, but just really quickly, for the given object, find the true shape of surface S. You know, there's two methods, of course. If we can see the surface and then we can see an edge view. If you can see an edge view, you can probably see a point view of a line. So this line right here that goes from 1 to 2 is appearing as a point view. 1, 2 right there. So if it's appearing as a point view, sure, we're kind of pretty sorted there. We can just rabat it down onto the ground. I'm not drawing them full now as full arcs for a reason. There is a purpose to that. Rabat them down onto the ground. And if I have them rabatted onto the ground, I know that their true position is they're rabatted in plan. And everything moves again perpendicular to the line in plan. So we get our true shape right here. There we are. That's the true shape of surface S right there. So that's T S of S. And the second method, if you see an edge view of a surface, you can look 90 degrees to that edge view, and the view produced will give you a true shape. If I'm looking at 90 degrees to an elevation there, I'm looking at a plan. So that x1, y1 is an AUX auxiliary PLAN plan. x1, y1. I certainly don't want to waste so much space up here taking distances all the way down from the xy, so I'm going to use a reference line right there. There's my REF reference line. And distances down, so the first couple of points are on the line. Okay, the first couple of points. So I already had labeled number 1 and 2. There's 3, there's 4, there's 5, and there's 6. Those 6 points define the full shape. So 5 and 6 are up top, 3 and 4 are here in the center, and 1 and 2 are on the ground. So what do we have? With 2 and 3 are on my reference. 2 and 3. We have 4 and 5 are at that distance right there. So 4, 5, and we have 1 and 6. 1, 6. And that's about it. That's all I'm really going to go through on this page as such. It's just a very, very quick look at these kind of questions. But again, just using rabatment or auxiliaries to find our true shape of a surface. So T, true shape of S right there again. So true shape found in 2 different ways. My preference is rabatment. I just think it's so much easier when you can see it. You can do it so quickly. Same story here. This surface can be defined there by 1, 2, 3, and 4. When we look down on top of that elevation, the line 1, 2 is appearing as a point, and also 3, 4 is appearing as a point. That's 1, 2, and that's 3, 4. So you can pick any one you want really. You can rabat wherever you want. If you can see a point, you have a line, you have a hinge. I'm going to use 3, 4 as my hinge. I'm going to rabat 1, 2. This really is kind of junior search stuff, I suppose. Rabatting 1, 2 there. It's like the chimney of the house in the junior search question, where I find the true shape of the sloped surface. Heights don't change. So the height of the point 2 there doesn't change as it rabats. The height of 1 still stays in the ground, and 2 still stays at the same height. And the main thing here is 3 and 4 never moved along the whole process. So that becomes your true shape of Q right there, all the way into the corner. So again, that's the one method. And the second method, which I'd say would probably be most people's go-to for this question, is looking at 90 degrees to the edge view right there. Project across with your 2 lines. Draw your x1, y1 line. And take your heights from the elevation. So 1 on the ground, 4 on the ground, 3 there, and 2 being up a little bit higher here, and just join the dots. Of course, not doing the messing I'm doing there, and using your sliding set squares or adjustable and compass. But anyway, 4 different true shapes shown there on the one page. Just that's right. The only reason I did it was just a quick little bit of revision there. And moving on to number 23, which I also did not draw on SolidWorks because I don't think we need to. These ones are kind of just laid in here as little extras. We're kind of getting on to the more interesting stuff again there in a few minutes. And onto some more difficult questions on oblique planes. But I just said I might as well breeze through these while we're here. But this one, determine the true shape of surface T. I suppose that's a tetrahedron there. One of those lovely questions. Determine the true shape of that surface. That's pretty easy. There's probably 4 or 5 different ways we could do this, and if you didn't get it, you're going to be kicking yourself after. Let's see. True shape of surface T. Well, do we know that it's a tetrahedron? I suppose we don't. If we knew that was a tetrahedron, that's the length of one of the sides. Well, the true length of that one up there, up from the ground up to the top of T, is also that size, and then the true length of the other one is that size. So that would be the question solved by just doing it that way. That would be nice if that worked. We don't, I suppose. We don't know it's a tetrahedron. That pity. That would be very handy if we did. Just want to make sure I have this all lined up correctly. Yep. And that point up to the apex. Never use a compass unless you have a line to use it on. So that's just the reason I wanted to add them up or link up them views right there. What I'm going to do is, first of all, I want to recognize one thing here. If I wanted to bring in the terminology I've been using all along, well, that line right there is the horizontal trace. It's the line that sits on the ground along the base of T right here. Here's the horizontal trace. If I look along the horizontal trace right there, I'll get a point view of the trace and I'll get an edge view of that plane. I'm not going to use a t-square, I'll just use a sliding set square for this. I'm going to look along that horizontal trace. And what else do we have? There's only one more point on the plane. There. Oh, while I was there now, I should have look along the trace and drop in my x1, y1 line. I need an edge view of that surface T. The height of the third point on the surface is there. I should label these, I suppose. That's point 1, that's point 2, and that's point 3. When I looked along 1, 2, I got a point view of 1, 2. Point 3 is the top of it right here. There's point 3. And what that gives me? That gives me an edge view of surface T. Edge view of T. 2 options. Go ahead and look at 90 degrees to the edge view. Take your distances back to 1, back to 2, and back to 3. That's your true shape. Second option. Extend on that ground line. And rabat. If I have a point view of the trace line, if I have an edge view of the plane, I can rabat. When I rabat, I can take my original projection angle and there we are. Bring it back. And I think what I'm after finding out there, determine the true shape of surface T. The true shape of surface T as point 3 moved out perpendicular to the hinge line. Well, the true shape of surface T is the whole plan right there. I could have found that on a separate diagram, or I could just find it on this diagram as I just did right now. That is the true shape of surface T right there. Just said I'd go through it just as a little extra, that's all. So we found an edge view and then we batted to get a true shape. This next page here, number 24, I've just actually changed the wording of the question a little bit. The great thing about these pages is if you want to do some extra practice and see how the answer should look, and practice a few different ways of doing this, you can just set up the page, you know, just on a blank A4, just go ahead and drop in your XY line and draw either the horizontal trace or the vertical trace, and then give yourself one more constraint. So in this case here, draw the vertical trace of the oblique plane, which is a true inclination of 55 to the, I just changed there, I want a true inclination of 55 to the horizontal, okay? I'm going to go through all of this really. Given that trace right there, I could work with a true inclination of 55 to the horizontal, which means that as my plane stands here, it's making a 55 degree angle to the ground. Or I could work with a true inclination of 55 to the vertical. As the vertical stands up, it makes a true angle of 55. I could work with any of them. On this one here, number 24, I've just changed the wording to draw the vertical trace of an oblique plane, which is a true inclination of 55 to the horizontal. And on page 25, the wording definitely was incorrect there. It said draw the vertical trace, which is already given. So, you know, that is just a little terminology mistake there. The vertical trace is already given. So draw the horizontal trace of an oblique plane, which has a true inclination of 70 to the vertical. So I just change that around there a little bit. Okay, so we'll pop back onto SolidWorks for a few minutes and have a look at just some of the methods we could use here, and page 24 being the main one to start with, given the horizontal trace and how we work with our true inclination. So back to SolidWorks for a while. Here we see the horizontal trace down here. We're missing the vertical trace, obviously. And the way that I've just changed the wording of this question, because I'd like to be able to show you the two methods here. I've changed the wording of the question to read, find the vertical trace of the oblique plane. So we're looking for this VT up here. And the oblique plane has a true inclination of 55 to the ground, to the horizontal. So, as I said, we could be given the true inclination to the vertical or to the horizontal. And what we'd start off with here, I suppose, what we're trying to think of is, if we had both traces, we have the horizontal trace as we see it in plan. It's a true length. If you looked along it, we get an edge view of the plane. We don't have a plane, but we do have a trace. So let's look along that trace anyway. Okay, so I've extended my top plane to accommodate a little bit more here for the auxiliary. I've extended through and viewed along the line, along the horizontal trace, and then I have drawn my auxiliary plane. I know that on that auxiliary plane right there, the true inclination that that plane makes to the ground or to the horizontal is 55 degrees. So I can draw a 55-degree line. So where's that now? Where are we? There we are. I'm pitching up an angle. So that's the point view of my trace, and I'm pitching up an angle of 55 degrees off the ground. And through that point I can draw my plane. And of course a plane is an infinite length, whatever size you want that fits on your page. We'll kind of just start linking it back to some of the previous methods we had here. You know, even when we were doing our rebatments, and even at earlier stages again in the previous set of videos. But what do? We usually take a point in the elevation of point P, we bring it down onto the XY line, we project it up, and we take the same height. So let's just do that backwards. Take a point, anywhere on your drawing, I think that's it right there. Bring it down onto the XY line, project it, bring it down to the X1, Y1, project it back down to plan, and then you can take it up the same height, and there they are linked up. Why does that work? Well, when I turn my view to see the point view of this line right here, you'll see that the points on the vertical trace line up perfectly. That means I can draw my vertical trace right there, and it means I can drop in my oblique plane. And that's that question finished. That has a true inclination. When I look along and see an edge view of the oblique plane, and I see an edge view of the ground, maybe not quite there, or something more like that. Right now I can see an edge view of the oblique plane, and I can see an edge view of the horizontal plane, so I can see the true inclination right there. That is one method. That's the auxiliary method. If you're given the horizontal trace and the inclination to the horizontal plane, well, there we go. Second method I'm going to go through now at the same time, not to be coming back to the video again, is here. Same horizontal trace given and the same question given. We've been told that this horizontal trace represents a plane that makes an angle, a true inclination of 55 degrees to the horizontal plane. This is what we can do. You can pick any starting point you want along the trace, and you can draw a normal. Okay, that normal then becomes the radius line for your semicircle. So any starting point at all along the plane, normal into the XY line, and we draw this all in plan, and then you draw your semicircle. And from there, from the side of the semicircle, you pitch off your angle of, in this case, 55 degrees, and you draw the elevation of your cone. So this actually is a cone. So the center point goes up, your 55 goes up to hit, and it can come back down the other side. So there's the cone dropped in. And there we go. And what I want to do next is I want to lean my plane up against that cone. And that cone has a base angle there of 55 degrees, which means any plane, such as this one here, which we're given the trace for, any plane that leans up against that cone has to have a true inclination of 55 degrees. That's about it for this one. Really handy method. So if it's leaning up against it, actually the one point I should probably go through right now, if it's leaning up against it, it's not showing me the sketch there. Where's my vertical trace? If it's leaning up against it, well, it has to be touching the apex. That's the only point we need to remember. So the horizontal trace is given. You go off with your normal and draw your base of your semicone. You pitch up your 55 degrees or whatever the angle is given at in the question, and you draw the elevation of your cone, and then just fit the vertical trace, touching the end of the horizontal trace and going up and touching the top of the cone. As a little extra here, the contact, the type of contact that happens between this red plane and this blue half cone is a full line. It's a full line going from the apex down to the point of contact that you set up in plan. So that might come in handy, it will come in handy for some of the later questions I'm going to be going through. So there's our full line of contact down through the object right there. I'm going to just pop back on now to sheet number 24, and then we'll get back to SolidWorks again before we go for 25. There's our two methods, an auxiliary method and the cone method. Now, what I'd like to also go through here very quickly is the way the question was originally worded was draw the vertical trace of the oblique plane, which is a true inclination of 55 to the vertical. And if that's the way it's worded, then we can also work with that. Okay, if it's a true inclination to the vertical, I'd have to set my cone up touching the vertical. So I just go the opposite way. I'd bring my center line of the cone here. I'd pitch off a 55 degree angle here, and I'd draw my half cone with the base touching the vertical. We'll get back to that one in a while though. For now, on to sheet number 24. So on this page, I'm going to try to get both methods in here on the same page if I possibly can. And I might even try to add in a third one right here, answering what they would have asked in the original question. So with the first method I just went through there involved looking along the horizontal trace, and that seems to be pretty perfect 45 degrees. I'm going to keep this really light now because I don't want this method to dominate the page. I think it's a very simple method. We're going on ahead as if we had all the information as usual, and then we're just going to go and use what they give us. They've told us that the inclination it makes to the horizontal plane is 55 degrees. So if it is, I can go from the point view of my trace right here on my x1, y1 line. And from that point view of the trace, I can just set up my protractor to 55 degrees. And up along that edge view of the planes, that's the edge view. That's the edge view of the oblique plane right there. And of course, if that's the edge view of the oblique plane and it's the edge view of the ground, then that right there is the true inclination to the HP, which in this case is 55 degrees. So from there I can go ahead, I can pick any random point at all. I'll call that point P. I can take the distance down to the ground there at point P. I'm going to keep this, as I said, really light now. I don't want this ruining the rest of my drawing. I can bring it back down to its position in plan, and then I can take the height of point P up to the elevation. Okay, that's the height of point P right there, up to the elevation, and specific height is here. There we go. That's the point on my vertical trace. So I can draw from that trace through that point and extend it on. That's the question finished using the auxiliary method. Now that's the auxiliary method, and I'm going to just lightly just rub that out for now and ignore it just for a few minutes. I might actually just bring that detail back in after, but I want to go through the compass or the cone method as well now. So I'd prefer the cone method for this. I think it's a very nice way of using, just dropping in a solid object there, a three-dimensional object, to solve a question for us. What I'll do, I'm going to start anywhere at all. I'll pick a point on the trace. I'm going to pick a point there, and I'm going to draw the normal at that point. And there's the normal. Next thing I need to do, I need to actually draw the base of the cone. So from the center point on the XY line out to the point in the trace, gives me the base of the cone. Now I'm going to carefully bring in my protractor again. From the point here to the left side of the cone, I'm going to draw the left extreme generator pitched up at an angle of 55 degrees. I'm only going to draw that up as far as the apex of the cone, right there. And I might just, for the sake of finishing off the 3D object, I'm just going to bring it down to this side, even though I don't need it. Finally, I can go ahead and draw the vertical trace, and if the plane leans up against the cone, well, it has to touch the vertex. And there we go. So that's the end of that question, and I think, if I'm right in saying, if I wanted to bring back in my original method I used there, it would fall, yeah, it's kind of falling on the center point. If I just, for the sake of noting it here, if I just took a different point right there, being the green point P, and I want the height of that from my end elevation, or from my auxiliary elevation, and I brought it down, what we should find, and I'll check this in just a second, is that the height of point P here is the exact same as the height of point P that was over here in my auxiliary. So let's see if that is the case. Is that the case? The height of the point P in my auxiliary onto the trace is the exact same as the height of the point P here. Yeah, that is pretty much perfect right there. So two different methods all on the same sheet. So we have our auxiliary method, and we have our cone method, or half cone method. What I also do now is I'm going to answer the original question that they gave here on this page. So we have our auxiliary method and our half cone method right there. I'm going to answer the original question that they gave just over here, maybe to the side, where I have a little bit of space. The original question that they gave, actually it was a 45 degree trace there, wasn't it? So this time we're going to answer the question of true inclination of 55 to the vertical plane. Okay. For a 55-degree angle to the vertical plane, we can't put the cone on the ground. The cone on the ground gives us a true angle to the horizontal. Wherever the base of the cone is where we're setting up our angle. So the base of the cone this time needs to go up here onto the vertical plane. I'm going to pick a point to start with, anywhere along here, let's say. Okay. Once I have that point picked, I'm going to draw the central axis of my cone. That's the central axis of the cone right there. I'm going to set up an angle of 55 degrees, so I might just use my adjustable this time, and set up an angle of 55 degrees here, and I can draw the extreme generators of the cone. And finally, I can go ahead and draw the base of the cone. So that cone that I've just dropped in ensures that this plane here makes an angle of 55 to the vertical. At junior cert you'd be expected to add in a full construction here for the point of contact. At leaving cert we're okay with just drawing the vertical trace as just a tangent. But what we would have to do here is, if we were asked for the line of contact or something like that, we'd have to use our sliding set squares off of the trace and draw the normal, which gives us the contact right there. That guy right there, then, that's the third part of this question page here. That's a true inclination of 55 to the vertical using a cone. What did I didn't put in one thing actually. If I just pop back onto this view here, the line of contact, the orange line in plan, that orange line in plan represents two things actually. It represents the original, just if we're talking 2D detail, it represents that starting line, it represents the normal that sits on the ground. But if we think in 3D detail, that right there is the apex, and it also represents the line of contact, LOC, and I'd just like to draw that in elevation as well. The line of contact in elevation is from the ground up to the apex is the LOC right there. So the line of contact that the cone makes with the oblique plane. Similarly up here, the line of contact is represented right there. But I'd also like to represent that line of contact in plan view, and of course that is a point of contact, so it has to be hitting that. That's on the vertical plane, which means in plan it's seen on the XY line, and the line of contact this time is here. So 3 different questions on the one page there. Just quite a bit in that now. So I hope that the SolidWorks model has really made it easy to understand. We've our 2 different methods, but 3 different questions answered. And make sure you take your notes of what you've actually been asked in this case here, especially for this one, so that when you're looking back at these sheets, they'll make sense. Sheet 25, and we're on to our second last one for this video. It's the good news. We're almost there. Sheet 25, now this one, as I said, was kind of worded a little bit off. Draw a horizontal trace of the oblique plane, which is a true inclination of 70 to the vertical. We're going to pop back onto SolidWorks, have a really quick look at 2 models of the, again, 2 methods. We have the auxiliaries and we have the cones. So we'll pop back to SolidWorks now for a couple of minutes. Vertical trace is shown here, so on the vertical plane, and we are told in the question that this oblique plane here makes a true inclination of 70 degrees to the vertical. And again, we could be given either way. We could be given the true inclination to the horizontal as well. As I said, I've changed the wording of this question. We have to find the horizontal trace, and we are given a 70-degree inclination to the vertical. Our two methods will work just fine again this time, and I've gone through both of them here in SolidWorks. So the first method is extend out there our vertical plane and project and view down through the trace, and that will give us a position for an X1, Y1 line and for an auxiliary plane down there. Then we use the information we're given, true inclination of 70 degrees. So we pitch off our 70-degree angle right here, and we pick a point. And you just basically pick any point at all. I've picked one right there. Pick a point and do what we did a few steps back. Bring it back down onto our X1, Y1, and that's our distance line, projected back up into our elevation, and then take that same distance line back down into our plan, which finds us a point on the horizontal trace. And as you can see there, when I get a point view of my trace line, I'm seeing an edge view of the plane, and I'm seeing that distance, in two distance lines, the yellow lines are meeting there, they're coinciding with each other. And the 3D method of doing that in SolidWorks would be just to project it straight back up from the auxiliary plane onto my horizontal plane. And then it's a join the dots exercise from there. Draw your trace out through that point that we found and define your plane. So that's our first method, and our true inclination being marked here. That is the true inclination that the plane makes to the vertical plane. And why is it? Because watch this vertical plane. As I look for a point view of the line, that vertical plane becomes an edge view. So if the plane is an edge view and the vertical plane is an edge view, this has to be a true inclination. Really, it's back to dihedral angles. That is, the vertical trace right there is the line of intersection between the oblique plane and the vertical plane. If you have a point view of that line of intersection, you have an edge view of both planes, which means you have a dihedral angle or a true angle of inclination. So that's that method. There's our oblique method. There's our auxiliary method, I should say. I'm going to go through that one on paper, but I'm also going to go through the cone method, which I'll show you here as well now. So there's the exact same vertical trace, and don't forget the question. Draw the horizontal trace, and this has a true inclination of 70 to the vertical plane, 70 degrees. So we need to do this. Again, pick a starting position and draw a normal, anywhere at all along the line. Once you have your normal drawn, draw your semicircular base. The base has to be touching the vertical plane for us to get our 70-degree angle to the vertical plane. So that's where the base goes. Pitch off your 70 degrees right there. And there's the solid object dropped in. That's the cone. Any plane now that's touching the base of the cone and leaning up against the cone has to have a true angle of 70 degrees to the vertical plane. That's our trace. Our traces always join up in the corner right there, and that trace from that point goes out and hits the apex of the cone. And there we go, that's our plane. So using our cone method, we drop in our plane, and I think I might have just added in the line of contact there. The red line is where the cone and the plane are in mutual contact. So that's the line of contact along there. Now that's it for this question here. Two different methods shown, our auxiliary method there on the left and our cone method, half cone method there on the right. So let's get back to sheet number 25 and let's solve it using both methods. Just to mimic exactly what we did there in SolidWorks and go with the same structure as that, we'll start off here with our auxiliary view method. So I'm going to line up my adjustable set square with this vertical trace right here. I'm going to view down through the vertical trace. I'm going to run off a 90-degree X1, Y1 line, and that X1, Y1 represents an edge view of the vertical trace right there. What's next? Next is the 70-degree inclination. So if I've looked down along the trace, I'm seeing an edge view of the oblique plane, and I can mark off my 70 degrees right here. That is an edge. I should put these in colour so they stand out a little bit more. That right there is an edge view of oblique plane. That is true inclination to the VP, which is 70 degrees in this case. Next, we want to pick our starting point anywhere at all you want, and I'm going to just pick this one right here, point P. We want to take our projection parallel to our original projection there, and we want to get this reference distance here for point P. We want to take it up to elevation and then back down to plan. And set off that blue distance right there. So from the vertical plane out to the point. Vertical plane out to the point. Vertical plane out to the point. And that's it. That's the question done. Okay. For the sake of it, you know what? Because I've only got 2 to do in total in this page, not 3. I'm going to leave that there. That becomes the horizontal trace, just for some extra notes in there so that you can see what's happening. That's the blue distance right there, out to point P, I should say. And that's our question answered. I'd like to answer it using the second method as well though, because you know we might as well just get it all there on the page and get plenty of practice here. So I'm going to go ahead and draw an XY line, and I'm going to draw a vertical trace somewhat parallel to what was already given there. Oops, ignore the top of that one, that never happened. And there's my VT. That makes a true inclination of 70 degrees to the vertical, so that's fine. Let's go with it. Let's set up first of all in line with the trace, and let's pick a starting point. Let's say here. Now whatever you do, don't go too small. Don't try drawing a tiny little cone here in the corner. It's so difficult to keep your accuracy if you go too small on these drawings. Set up the rest of your cone by using that normal as a radius line. Angle has 70 degrees, so I'll set up this guy here to 70. This is about to get pretty big here. 70 degrees, yeah, that's a pretty large drawing right there. And there's the center line of the object. Right there, going down, catching the apex. And the horizontal trace must be touching the apex. So there we go, HT. What's left? The line of contact. I might just drop that in there as well. And there it is on the vertical plane. So bring it down to the plan, onto the XY line, which is the vertical plane and plan. And draw your line of contact. And there's your half cone method. Now, we're getting there. We're almost at the finish line for this video. The only thing left now is one final question. That right there on page 24 and 25 really does give us the basis even for our next page, which is a little bit more difficult. But 24 there, true inclination to the horizontal. Given the horizontal trace and given the true inclination to the horizontal, we have our auxiliary and our half cone. Given the horizontal trace and the true inclination to the vertical. This time, given our vertical trace and told the true inclination to the vertical. If you've made it this far, well done. We're on to page 28 now is our next one. 28 gives us, a lot. Actually, it gives us very little. Draw the traces of an oblique plane which has a true inclination of 60 to the horizontal, so it stands up at 60 degrees to the ground here, but it has to also have a true inclination of 45 degrees to the vertical. So that's it. There's nothing else given, just the two true inclinations. And I think when you look at this originally and you look at the page, it's just an XY line and two true inclinations, and that's it. And it's kind of hard to see what to do next, you know. The only thing that is given is the words quarter sphere. So we go ahead and we draw a quarter sphere. Let's not question it. Let's just go with it. We'll draw a quarter sphere. So there's a quarter sphere dropped in. I just did a semicircle and rotated it down by 90 degrees there. Dropped in my quarter sphere into the corner. You can see all the other objects at the back. Actually, it looks quite good. We need another oblique plane in here. And I suppose as you might have guessed, we're definitely going to use some cones here. Look, we'll go with it. Okay, we're dropping in a quarter sphere, and there's a very, very good reason for that. That quarter sphere will allow me to structure two common tangent cones. So I want a cone to sit around this sphere. And first off, I want that cone to have a true inclination of 60 degrees to the horizontal plane. So that's the first cone. All right, so I'm solving this question one step at a time. That's the base of that blue cone, and there's the blue cone. And SolidWorks does this kind of a sharded effect here when there's two solid objects in contact with each other. So it doesn't give us the exact circle of contact. It kind of just shows this shardy effect. It knows that they're touching. It doesn't know to what extent, I suppose. But there is a 60-degree inclination of a cone right there. So if I decided to make my trace along here, my horizontal, and lean the vertical trace up then to touch the apex, well, I've solved one half of the question only, but it might not be the right plane. It probably won't be. That's the first half anyway. So 60-degree cone touching our quarter sphere. Before we do this though, we have to recognize what does a quarter sphere look like when we draw it on our page? Well, it's a semicircle in elevation and it's a semicircle in plan. So it appears as a full circle. So that's the only thing we need to recognize. The size of it doesn't really matter. Again, if we go too small, it's hard to keep accuracy. If we go too big, it'll go off our page. So we'll have to have a think about that one. The second thing that they told us is that it has a true inclination of 45 to the vertical. So we go ahead and we work with that, and we try our very best not to let this confuse us now. Down in plan, we have our true inclination of 45 degrees to the vertical. These extra lines here give me my point of contact. A 45-degree tangent has a 45-degree normal. Up in the elevation, our 60-degree tangent has a 30-degree normal coming out. The next job is there with my green detail. That's the 45-degree inclination to the vertical. Draw the base of the cone. And for me on SolidWorks, draw the cone. Now, if I can find the one plane that touches both cones, then I will solve this question. First off, it has to touch this point, the tip of the green cone, and it has to touch the base of the blue cone. So we can go ahead and draw the line that touches the apex of the green cone and the base of the blue cone. If I apply the very same rule here, it has to touch the top or the apex of the blue cone and the base of the green cone. Let's just hope that it lines up perfectly with that point. And if it does, there's our traces. So, touching the apex of one and the base of the other, apex of one and the base of the other. That means that it's in mutual contact with both cones. If we can just visualize for a second that the line of contact, and I'll drop in the oblique plane in just a second now and we'll move on to the last part. The line of contact that this oblique plane makes with the green cone goes from the point here right up to here. Is that the same as we had before? It is the exact same as we had before, the line of contact. So if we were able to just pluck the green cone out and the red traces out, well, there they are. For the blue cone, the line of contact it makes goes from the apex up here right down onto the trace down here. And where did we see that? We saw it back here. The blue cone right there, and our line of contact going down to the normal on the base. So that's satisfying both criteria that we were given: 60 degrees to the horizontal and 45 degrees to the vertical. And there's the oblique plane. The only little extra that might actually be dropped in here for us to solve is to find all the lines of contact, or find just one single point. Like getting back to this quarter sphere here in the corner, that quarter sphere, if we can just about see it now with all the planes and lines, it comes out and it touches the oblique plane at one point only. So that might be something we'd be asked to find the point of contact between the quarter sphere and the oblique plane. So here we go. Here's the first thing I've just drawn. Okay, I've drawn my normals first of all. There's one normal right there, and that normal gives me, oh, sorry, I'm onto my second normal first of all. There's the normal right there. That gives me my line of contact that the plane makes with the green cone. And then, as you can guess, the line of contact that the plane makes with the blue cone. Watch this point, okay? There's a lot happening at this point right here. I have not right now found, so this dashed line down through here is this one, the red one here. The line of contact that the oblique plane makes with the green cone. And then there's also the line of contact that makes with the blue cone. But what else is going on here? What else do we have? That blue semicircle right there represents the circle of contact that the blue cone makes with the quarter sphere. And watch the way it goes around there in the middle of all those kind of shards, and it touches right on the same point that the two lines of contact are meeting. And if I had one last one now, the circle of contact here, where the green cone is in contact with the quarter sphere. That's the last one. It comes from this point of contact here. And there we go. Everything coincides in the same point. That right there is the point where the oblique plane is tangential to the quarter sphere. Now that is getting a little bit into it now, but that is everything you need to know about your quarter sphere. Let's get back to paper. Let's get drawing this, and we'll get this tutorial finished. Right now, my compass is set to 40 millimeters, and I think that's going to fit pretty well. I'd like to start anywhere at all here in the roughly around the center of this line, maybe slightly off to the right there. And as I said, the compass is set to 40 now. This quarter sphere is a semicircle in elevation, and it's a semicircle in plan. So there we go, that's my quarter sphere. And as I said, for this question here, just the fact that it's on a small A4 page, I have a radius 40 in my quarter sphere. The colours, I'll stick with the colours I had. I want, first of all, to draw the trace of an oblique plane that has a true inclination of 60 to the horizontal. I'll do that first. If I want my 60 to the horizontal, the first thing I'll do is I'll go 30 out as a normal. Because I'm using fine liners, I'd like to know exactly when to stop. 30 out to the normal, and 60 up with my tangent like that. Go ahead now, and I'm going to just draw the base of that cone that's inclined at 60 degrees to the horizontal plane. And that should give me the second side of that cone at 60 degrees. Do I really need to draw it? No, I don't. But I think it looks good to have it in there. And there's the normal, of course, as well. So that's that cone dropped in. Now, I should not be doing this. You should never really do this, but I just don't have a compass with me that I can drop these fine liners into, and I really want to show the difference between all the curves that are happening. Right there, we have our blue 60-degree cone. Okay, so that's the first part of the question. As I said before, any plane we draw that is in contact with the base of that cone and goes up and hits the apex will satisfy the first part of the question, true inclination of 60 to the horizontal. What are we on to next? We're looking at a true inclination of 45 to the vertical. Again, I'll stick with my colour scheme in case you're flicking over and back to SolidWorks. True inclination of 45 to the vertical. Let's go for that one. And the reason I put the few blue dashes is I don't want to go and work with the wrong curve here in plan. True inclination of 45 to the vertical, so I need to go off 45 one way. Again, just because I'm using my fine liners, I don't want to go too far with this. So that's going to be the apex out there someplace. And there's my true inclination of 45 to the vertical right there. I can go the opposite way as well. And I get a perfect apex on the center line. And there we go. I can open up the compass, and before I draw it now, I'm going to just check it and make sure it's falling perfectly, and if it is, and there we go, that's the base of the cone resting on the vertical plane right there. And again, even though I really don't like doing this, just for clarity I might just drop it in there. So there's the two planes, or the two cones dropped in. This question, this XY line is looking a little bit short for a question this size. So let's go ahead and let's do what we saw in the SolidWorks there. So keep flicking back to that part of the SolidWorks video if you need to. I'm going to draw the horizontal trace, and it has to be in contact with both cones. So it has to touch the apex of one and the base of the other. I'm going to do the same up here. It has to touch the apex of one and the base of the other. And it just falls perfectly, touching the second trace right here. And there we go. It's the traces. We've answered that question right now, but I'm going to just take it on a step further. VTH, given right there. We have actually answered the question now. On my little notes here, we have our green 45 degree cone. I'd like to find the full circle of contact, and I'd like to find all lines of contact, and I'd like to find the one single point of contact that the sphere, the quarter sphere, makes with the oblique plane. So let's keep going on this for another little while. First off, I'm going to set the angle of my horizontal trace right there, and I'm going to draw a normal out, which will give me from the center out to here. I don't even know what type of line this is. I'm just trying to signify it in some way out from the others, but that is the see the line of contact right there. Now where is that in the elevation? So that's the line of contact that the oblique plane makes to the blue cone right there, and in elevation that line of contact is there. That's the line of contact, LOC. Up here in the elevation, set my vertical trace and find my normal. That is the LOC again. And where is that in plan? And there we go, LOC again. Now this is starting to get quite crowded here, but what I do need to recognize is this. I need to recognize that that point right there is the common point between the lines of contact, which is also here. Okay, the pink point is the POC of the quarter sphere, and oblique plane. Okay, that is the common point of contact with the quarter sphere and the oblique plane. The very last thing, and if you don't feel like putting this in, then don't, okay? I don't want to over complicate, which I probably, that ship has sailed. I think I've over complicated already, so you know what, in for a penny, in for a pound. We'll keep going. Right there, from the normal, right across there is a circle of contact. Circle of contact from the blue cone, blue 60-degree cone, and the quarter sphere. And that full circle of contact can also be brought down to plan and drawn as a circle of contact. And what we'll find is, just as I showed it on SolidWorks, I want to show it here as well. That full circle of contact right there. And let's hope my accuracy won't let me down here. That full circle of contact. There we go, that's good. It works. That full circle of contact there hits the pink point. Okay, so it hits that pink point perfectly. So it's not by coincidence that everything just happens to line up perfectly. It is all the way it's supposed to be, and that's the whole principle behind this quarter sphere. The circle of contact between the blue 60-degree cone and the quarter sphere catches point. I'm going to call that point P, I suppose, right there, which is also here. And the final one, if I haven't confused you yet, I will now. I'm definitely going to. The final one, the circle of contact that the green cone makes, right there. Circle of contact from the green 45-degree cone to the oblique plane. Sorry, to the quarter sphere. I'm even confusing myself here at this stage. That is the circle of contact that the green cone makes with the quarter sphere. Also touching perfectly through point P, and if we take that up to elevation, and there we go. We take it up to elevation and we draw that circle of contact. Now, talk about a sheet of overkill. That right there is the circle of contact that the green cone makes with the quarter sphere. Pop back onto SolidWorks to try and make sense of all of that. There's so much going on in that page, but it just, it's just every eventuality is covered here now. We have our lines of contact and lines of tangency, we have our points of contact on the traces, we have our circles of contact from the spheres to the cones, and we have that final point P right there, the single point of contact that the oblique plane makes with the quarter sphere. Everything there in one page. I hope this video helps. If you've made it this far, then you've a very determined person. Fair play to you. I hope, as I said, I hope this video helps there. There'll be one more coming on plane and descriptive geometry. This really is the one that covers the most of the bulk. The first video kind of was the basics. This is kind of bringing us to the real higher level stuff, and the next video will just cover the last number of pages in this series of worksheets. Thanks very much for watching.